So the next speaker is Jaakko Nissinen, talking also about gravity in Weyl systems. So please go ahead.
Okay, so thanks for the organizers for this extremely interesting workshop. And basically, I got the talk inherited from Grisha Volovik, and I'm happy to basically present my work because it's heavily influenced by the old, in my opinion, groundbreaking work is done on many of the subjects of the conference. And on the other hand, the subject also fits very nicely into the overall theme, and also basically the questions proposed by the previous speaker, which I think are very good. And of course, well, in some sense, since we're dealing with emergent fields and emergent physics, the truth is always somewhat in the eye of the beholder. But in any case, basically, the real benefit actually is that we can really probe interesting gravitational physics using basically properties of condensed matter media. So the outline of my talk is the following. So basically, I will introduce Weyl fermions from my perspective and basically fix the notation I will use later on in the talk. And the organizers asked for basically a provocative talk, which would address any remaining or interesting open questions in the field. So basically, I decided to put the question into the title of my talk, and I finished it with a question mark. But given the sort of caveat of emergent gravity, I think from my personal point of view, the picture is sort of consistent, and I would kind of would personally remove the question mark, but let's see how other people feel about it. So I will basically speak about chiral anomalies induced by gravity, and basically a more exotic or more rare example of gravity than what is usually found in nature in general relativity. But nevertheless, it has a kind of a long history, and the history is kind of controversial. But I will present 3 examples of systems where I believe that torsion is relevant for the anomaly, and basically they all feature a different approach to the anomaly. And kind of the standard thing what you have in this business is that you have many ways to calculate the anomaly, and they are all kind of independent and depend on the different ways you regularize. But on the other hand, if you manage to kind of get similar, or at least well, similar, if not exactly the same answers by using different approaches, then to me that's kind of a thing that you should expect, whether you want to kind of make statements that it's actually real or not. And if you want, you can take the first approach to be kind of the Fujikawa's method with path integrals and anomalous Jacobians. Second method is the kind of thing already spoken by Carl Sieve, meaning spectral flow in the presence of Landau levels. And third thing, which I will briefly mention, is anomalous Kubo formulas with torsional backgrounds. And okay, the real subject of Carl Sieve's talk was chiral kinetic theory, and that's still kind of missing from this list, but you could still say that this kind of torsional Landau level spectral flow approach is basically the Pullman's way of obtaining the same kind of distribution functions. In the Landau level case, they're one-dimensional. In the chiral kinetic theory, they're kind of 3-dimensional, basically incorporating the full system, not just kind of one particular configuration. And the talk is based on the following papers. And as I already said, some of them are with Grisha-Volovic, but in overall, the talk is heavily influenced by his old work on chiral anomaly in superfluids and superconductors. And please interrupt me with questions while I'm speaking, just to make sure that we can proceed with kind of minimum confusion. So just introduction to Weyl fermions. What are they? Basically, you have some fermionic system with any kind of two bands crossing at a point. And the point is that that's kind of perturbatively stable in the sense that you have three constraints and three parameters, because any two-level system you can present in terms of the Pauli matrices. And in order to have it, you need to basically break inversion or time reversal symmetry. Additionally, you can have more complicated crystalline symmetries that stabilize them. And okay, when those symmetries are not broken, you can have more bands crossing at the same point, and then basically you have a Dirac point. And basically already these old works introduced this observation, but what has happened more recently is that the whole business kind of exploded with the discovery of Weyl and Dirac semimetals. And yeah, so I've already here indicated basically the basic coefficients of this expansion. And of course, in a real condensed matter system, you don't have linear dispersion. So in principle, there's always kind of this higher order piece, which is left out from the low energy consideration. And usually it's just considered to be irrelevant, but basically kind of what I will be speaking about is this missing pieces from the linear Weyl description. Right. So to pinpoint basically the gravitational fields or the emergent gravitational fields that I'm speaking about, let me just present it in this way. So this is the linear Weyl Hamiltonian. And from this expansion close to the node, we immediately get this effective tetrad or Vierbein, or more generally Vielbein fields. And basically in just the same sense as in real gravity, they basically determine the shape of the dispersion, which is near the band crossing. And basically this was already mentioned by the previous speaker, that indeed this kind of immediately gives you at least some access to gravitational physics. And what is also interesting is that the low energy capless fermion in this system with the finite node shift is actually already something which kind of involves very heavily the chiral anomaly, in the sense that you need to kind of rotate in momentum space your original fermion in order to get access to this capless fermion. And basically this is the same point which was mentioned by Anton Burkov in his talk, meaning that properties of the chiral anomaly are actually basically stabilized or protected by this translational symmetry involving the node shift. And all of what I'm going to say is heavily relying on the fact that this node shift is finite. And of course, if you go to a real relativistic system, the node shift is just zero by Lorentz symmetry. And on the other hand, based on the symmetries that I just briefly mentioned in the previous slide, in a condensed matter system, you generically always expect that the Weyl point will sit at some finite momentum, basically determined by the symmetries that you're using to fix it. So,
question. You said you call this metric and tetrad. Tetrad refers to 4 basis vectors, but it looks to me like you're just talking about the 3-dimensional geometry. Is that right?
That's correct, but in some sense there's no restriction, and this is, I mean, Okay, so this is the Hamiltonian perspective, but nothing prevents me from going into the Lagrangian description. And there,
right, but how would you? But which physics would alter the time components of the metric from your viewpoint?
From my viewpoint, the obvious one is say superfluid velocity, and also you can imagine other Weyl systems where you have non-zero velocities that will directly give you a non-trivial E naught. And similarly, based on the previous talk, in the simplest sense, the Lucifer or the Tolman trick, which is basically giving out gravitational fields from thermal gradients, that's also introducing a non-trivial E naught. So it's not as natural in condensed matter, but on the other hand, it's not, I mean, it appears, or non-trivial components of E naught also appear in condensed matter. Right. So just by looking at this Hamiltonian, it basically, well, it involves the gravitational fields or the emergently gravitational fields, and it also involves the node shifts. So basically the obvious question now is that, are there chiral anomalies from emergent tetrads or gauge fields in condensed matter? And finally, also slightly related to the previous question, is that indeed for Weyl fermions, they only exist in 3 dimensions. So if you're interested, you can also check a nice paper by Horava from 2005, where he basically shows that whenever you have a Weyl node, in the sense that you have the topological invariant describing it's non-zero, you always at low energy end up with a Dirac-like spectrum. And basically that's what he derives, and that's linear, that's up to linear order, but all the higher order terms are then basically fixed by the microscopics. And kind of a formal way to say what I'm doing is that I'm basically deriving the or contributions from the higher order terms in specific examples. Right. So another thing which I should also mention from the outset is that I will be talking about the geometric deformations, and 2 examples I will have are, well, the chiral superfluids and superconductors, and also strange crystals. And also relating to the previous talk, it's indeed kind of what you can show, that if you have some lattice, that's basically introducing a preferred frame in your space-time, but then you can just go and deform it. That's very easy in a condensed matter setting. And this deformation at the level of linearized elasticity will basically give you the effective dry bind, Vierbein, or Weyl binds. And this needs to be kind of carefully checked in a semi-classical expansion, because of course this undeformed Weyl Hamiltonian is kind of in a setting where momentum is a good quantum number. But in any case, there are many papers which are basically performing this expansion, and that's basically a nice result. And now all of the things that I'm also speaking about should always be kind of contrasted with these pseudo gauge fields. And this is basically arising from the following fact, that if I assume such a geometric deformation, basically what's happening is that this dependence on the Fermi momentum is cancelled, which is shown here, just because of this kind of initial assumption. And if I now go here at the question mark, I go and expand this Hamiltonian just near to the Fermi velocity, Fermi momentum, that is the Weyl, the momentum where the Weyl node is sitting at, I immediately obtain basically a gauge field with a momentum charge and the remaining dependence on this effective tetrad or the emergent tetrad is basically second order in smallness, because it's the small momentum close to the node times the small variation of the geometry. So this immediately gives me the kind of pseudo gauge field from the Fermi momentum. But when it comes to the anomaly, I think it's very important that it's kind of realized that the anomaly from the tetrad must be different than the anomaly from the gauge field. Basically, it's kind of the difference between gravity and gauge fields. So the second one is universal in the sense that if you have a charged state, it will always flow universally. On the other hand, in kind of this emergent business, the charge is also emergent. In this case, it's just the momentum sitting here, but this momentum is not universal in the sense that you have many states with different momenta, and then they will flow differently or react to the fields in a different way. And
question, just why in your expansion, well, with the pink arrow, why don't you have any delta AI with the KW? Where does it disappear?
Well, it disappears in this assumption. So all the deformation of the Fermi momentum is introduced by the tetrad, but experimental access is not to this guy, but rather to this guy. So if you go to the laboratory and look at this deformed crystal, this is the guy which you're having. So that's definitely changing, but the change is kind of the geometric one, and that needs to be taken into account in this case. And basically this holds by definition in the chiral superfluid or superconductor, just because of the structure of the Fermi surface. And okay, there are many papers which basically take this starting point or derive this property. So it's not based on my work, but it's rather kind of quite general. Okay, so let me now go to the anomalies. So this has been already discussed by various people. So, but let me just briefly mention that indeed this is the Adler-Jakiv chiral anomaly, now written for a single chiral complex fermion, which always will have it. And this is the standard piece. And also the previous speaker was basically mentioning that quite surprisingly, even this gravitational piece is affecting condensed matter systems. And there are many papers discussing this, and that's of course fine. All those results are very much true, but there was always kind of this lingering confusion that how can this term be relevant since it's actually fourth order in gradients, and in any condensed matter system where you're doing basically perturbations to some homogeneous background, I would say it's impossible to kind of detect this directly. That's of course with the things mentioned by the previous speaker, that the gravitational fields needed here must be kind of enormous. And on the other hand, I cannot just, I mean, I will need to have some emergent fields basically playing the role of gravity if I want to basically probe gravitational anomalies in a condensed matter system. That's opposed to the basically theoretical approach where you take some theory and then you derive interesting correlation functions or interesting properties by basically coupling it to a geometry, but then setting the geometry to the flat space at the end. So the kind of emergent nature of these fields is very, very important, because otherwise I wouldn't have physical fields which would actually be playing the role needed. And okay, this thing I basically said that this just vanishes because it's fourth order. On the other hand, this torsional piece is second order, likewise the gauge piece. But also what I just also already told you that I will not be considering any types of gauge fields. Instead, all of the dependence is basically in this tetrad fields. So this guy here is the same thing which was appearing in this low energy expansion. In addition, you have the spin connection, which, okay, that's another discussion. When could you have that in a condensed matter system and when not? But in any case, the tetrad field universally always appears in any condensed matter system, just because it's basically the expansion coefficients of your Weyl Hamiltonian, and then you just need to deform them in order to induce interesting torsion. The interesting point here is also that we are very used to having a metric and connection derived from some metric, but here it's also kind of mysterious that, okay, this is basically directly physical, but in what sense should you fix this torsional connection? Because basically, when you have non-zero torsion, the metric and connection, or the tetrad and connection, are independent. So what should be the physical principle that would fix such a torsionful connection? And okay, I have a few examples, or basically one example about that. But anyways, let me now basically state the main result, which is the following expression. So just by dimensional reasons, the difference of this torsional gravitational anomaly to gauge anomaly is given by the fact that in canonical relativistic units, this guy, in order to contribute to the anomaly, will need basically a momentum scale squared appearing, or just the same, you could have a temperature or chemical potential appearing. So what's the nature of this mysterious scale in the anomaly? Because first of all, it will make the anomaly non-quantized, because basically you would need to have this, and there's no reason why it would be quantized. Second one is this kind of really weird, from anomaly perspective, that you have a high energy scale appearing and then you have a low energy scale appearing. So that's very weird. And basically, the short answer to all of these questions is that in a condensed matter system, you always have such a UV scale. And that UV scale is simply provided by the underlying condensed matter system. And similarly, you have also many different low energy scales, which can contribute independently. And as I already said about the real relativistic torsional anomaly, I will not have anything new to say. Basically, it really looks like that this is not well defined, and it should just disappear. And actually, if you maintain Lorentz invariance, you have a UV counterterm available, which is basically subtracting this contribution out. But on the other hand, this kind of finite temperature, low energy contribution seems to be consistent with other results as well. And okay,
can I ask a very quick question?
Yes.
Just nitpicking, but in this equation, you have on the right-hand side, you have differential four forms, and on the left-hand side, you have something which naively looks like a scalar, or maybe this is a Hodge star.
Yes, so I apologize for the imprecise notation. And
no, it's not about notation. I just want to ask, the current fundamentally is a three form, and in order to convert it to something like what we are used to, a current vector, we usually need something like Hodge or raising and lowering. I mean, I want to ask if your tetrads appear also on the left-hand side in some sense.
It appears, and it appears in this kind of, this is basically, this is not well-defined notation, but this star is basically, there just to make it consistent with the right-hand side. So
Okay.
what happens is that with torsion, the connection is such that the physical current is not the vector current, but it's the pseudo tensor current. So there's a factor of determinant here, and okay, this is differential form. So basically, there's equal. Yeah. So basically, short answer is that. So this is a differential form, and this is the one associated.
And the tetrads float around on both sides of the equation somehow to make this.
Well, this is a differential form, so it's coordinate independent, except for the explicit appearance. But okay.
Yeah.
I mean, go to any paper and basically, well, not any paper, but you can insert all the proper factors.
Okay, fine. Yeah. Thanks.
Right. So, and well, just based on the previous talk, I mean, the structure of this anomaly is precisely so that you would expect it also already in flat space, in the sense that this temperature is appearing here, and you can introduce gradients, which will basically also contribute. But anyways, now I'm already kind of running out of time. So let me now go to the actual physical examples. Okay, there's a question, so maybe we should take that.
Sorry, quick question. In the condensed matter setting, beyond the cutoff introduced by the band, there is also surface states. So can you say something about what is the role of the Fermi arcs with this anomaly? Because in principle, for the current anomaly, they can also kind of short circuit by connecting the two nodes.
Well, that's an interesting question, and okay, that's slightly different in the sense that if you really want to kind of connect surfaces, say top and bottom, you usually put in a magnetic field with charged particles. But basically, I'm not including electromagnetic fields, and from my perspective, particles could very well be just neutral. They don't need to be charged. And regarding the Fermi arcs, it's all, of course, slightly problematic because this kind of low energy disruption will break down near the surface, in the sense that this Weyl node is not, I mean, basically the node momentum is somehow disappearing or having a jump when you cross the surface. So it's not, one should kind of carefully devise a proper setting where this is analyzed. But in this 2016 paper by Adolfo Grushin and collaborators, they discussed the Fermi arcs in terms of Landau levels, and basically I think that's a fine discussion, and what I'm saying is not kind of directly related to that, although I would envisage that you can describe, I mean, you can describe the Fermi arcs also in a gravitational setting, but okay, needs to be done, but yeah, basically a separate question.
Thank you.
Okay, so the first example is really
just another question about your last comment in the previous page about Luttinger. Considering only a Luttinger metric or a Tolman-Ehrenfest-like metric, is the Nigan form really non-zero? Because I'm not sure it can be non-zero if you consider only the Luttinger metric, which change only one coefficient of the tetrad.
Well, the form will be non-zero in just the same way as I mean, basically it's the time-like torsion piece is well, logarithmic derivative of your temperature gradient. So that works just the same as with the metric. So that's the short.
But the wedge product will be non-zero also, the TA wedge TA, because if you only have one, which is modified, the wedge product will be.
Okay, I'm not sure if I'm following it, but the short answer is that this Luttinger field will enter the time-like torsion. And okay, you can actually show that if time-like torsion is non-zero, then you don't have a global description of time coordinate. And that's already kind of weird, but okay, as a mathematical trick, it works. But short answer is that basically logarithmic derivative of temperature gradient will enter the torsion piece. So if you want, you can have a look on this paper where it's kind of shortly and not very carefully discussed. But let me now try to continue. If I may, can I? How much time do I have left?
I think you have approximately 5 minutes. So may I also suggest that maybe we keep questions for Jaakko until the end from now on, so that you can perhaps first finish. And
So
then...
is the 5 minutes including the question time or not?
So if you finish in 5 minutes, then there is, let's say, 10 minutes for questions roughly. If you finish in more than 5 minutes, there's less time for questions.
Okay, let me try to finish in 10 minutes or so. Okay, thanks.
So you want to negotiate about your time?
Well, I already answered a couple of questions, so I think...
I include that. But if you finish at least in 5 to 10 minutes, let's keep it at that. Then there's some time for questions, and then people who may have plans otherwise can at least see your entire talk. Yeah.
Okay. So right. So yeah. So the first system where this is relevant is the chiral superfluid in time reversal breaking chiral superfluid P-wave system. So there you can immediately kind of see that there's funny business going on with both angular momentum and linear momentum. And actually, if you study the system, you can see that kind of the local angular momentum density is kind of vanishingly small based on what you expect. And that's basically based on the fact that you have Cooper pairs, which are kind of sparse. And then because of the nodes in your gap, you also have unpaired quasi-particles. And basically they're all flying around and making the angular momentum not well defined. And from this, it follows that actually you can define the variations of angular momentum and linear momentum in a well-defined way, but then the linear momentum of each subsystem is not conserved, in the sense that linear momentum is transferred from the condensate to the quasi-particles. And this is really a manifestation of the chiral anomaly. And in terms of the hydrodynamics of the superfluid, which is a very well-defined concept, you can immediately write down the equation. And okay, the essential pieces which are entering here is the kind of combined orbital gauge symmetry, which is resulting from the gap function, and also the kind of hydrodynamic properties of the P-wave system in this case. And what's important is that you actually have an anomalous piece of vacuum mass current, which is kind of appearing from textures of this unit L vector, which is describing the superfluid or superconductor. And this is basically the anomaly equation. And now I want to relate this to the chiral gravitational anomaly. And I can just take the low energy effective field theory in the presence of both texture and superflow, which is basically the ingredients that I need for this anomaly to be non-zero. And then I can write basically the semi-classical Bobelnikov-Digens equation, and then I arrive that it exactly looks like a Weyl, relativistic action of Weyl fermions coupled to geometry, and the geometry is basically determined by these, by the gap function. And if I now look at this emergent spacetime which is resulting, I immediately see that it basically has an interesting tetrad and actually also an interesting spin connection given by this expression. And basically by these hydrodynamic relations, I immediately obtain both non-zero torsion and also non-zero curvature. And if I now map the kind of original U1 symmetry of the fermions to these quasi-particles, I can write it as a planar local Lorentz symmetry, which is featuring basically a torsionful energy momentum tensor. And this is basically the indication that this is really kind of a okay description of the low energy.
Jaakko, I think you just slipped for, had a glitch for 30 seconds or so. I don't know if that was only me or other people had the same problem.
Here it was okay.
Oh, okay, sorry.
Okay, so let me now rush to this kind of final point related to this system, which is that if I now write the kind of linearized energy momentum tensor, I obtain this type of a form. So basically this latter piece is not interesting because it's basically coming from this torsionful geometry, but because it's a condensed matter system at finite momentum, I get this piece, which is basically proportional to the node momentum and also to the relativistic current. And this is for one node. And when I combine them, the conservation equation immediately gives me kind of the chiral anomaly in the sense that this current is not conserved. And if I now just match it, this hydrodynamic anomaly to the hydrodynamic anomaly in the superfluid, I immediately obtain that it's given by the proper expression where this dimensionful UV scale is basically given by the validity of this linear Weyl approximation in the low energy theory. So in other words, this scale appearing in the anomaly is very natural. And indeed, it was kind of discussed in the high energy literature also. I mean, this, as far as I know, this is the first explicit value for this coefficient, but the fact that it should be related to the basically breaking of Lorentz symmetry and breaking of the Weyl physics. Right. So I should emphasize that this has been experimentally observed, but that's basically, if you're interested, you should perhaps ask Grisha Volovic about it. Okay, and I can basically do the same calculation with torsional Landau levels. And in this case, again, the kind of important point is that it's a condensed matter system. Because if I compute the anomaly in a relativistic system, which is sitting at zero momentum, I immediately kind of discover that indeed, if I would like to have a non-zero anomaly, it's basically only sensitive to this high energy cutoff, in the sense that I could say that here states are or holes are disappearing beyond the cutoff, and here particles are disappearing beyond the cutoff. But that's all. And because of this momentum dependence related to these tetrad fields, these states don't flow uniformly, but rather in proportion to the momentum. But now, if I do the same calculation with at finite momentum in a condensed matter system, I kind of obtained a similar but entirely different picture where this anomaly can be well defined. And indeed, because this separation is happening in momentum space, it's basically giving me a finite amount of momentum transferred at low energy. And momentum is kind of globally well defined, so I should match it to some, I mean, momentum must be conserved in the end, so there must be somewhere else where it's going. Right, and this is basically the linearized spectrum, but in a real condensed matter system, it should be parabolic or something similar. And okay, the overall picture is similar, but there are some differences. And I should mention that this is basically an example of an anisotropic Newton-Cartan geometry. But the overall result is actually the same when I apply it to the superfluid or superconductor. And here is the Landau level calculation in more detail. And basically the difference to gauge field is sitting here, where just because of this momentum dependence, I basically, in order to obtain the spectral flow, I need to integrate this momentum dependent density of state in some finite window. And that's basically producing this scale. And indeed, this calculation matches the one which was actually found just by matching the superfluid hydrodynamics and the kind of Weyl anomaly. And okay, there's some important differences when I go to finite temperature, and then I will find this T² piece, which also contributes to the anomaly, and also that matches the superfluid hydrodynamics. And okay, same thing can be applied now to this strained Weyl semimetals, where actually deformation of the Hamiltonian is naturally described in terms of these tetrads. And then the real kind of question is indeed that compared to gauge fields, there will be this suppression given by this geometric factor from momentum space. And the real question is now that since this is small and you input all the microscopic parameters, what will be the end result? Will it be small or not? Can it be measured or not? Can it be observed? Which one is correct? Anomaly from torsion or anomaly from gauge fields? Right. And finally, I should also say that all of what I've said can be connected to relativistic Kubo formulas with torsion. And presumably, Carl Landsteiner might talk about this. So let me just leave it like that and go to my conclusions. And before I finish, I should flash also that, okay, if you're interested, there's some related work about condensed matter torsion, which basically would require a separate talk. And the stuff that I was talking now is in these papers, with the last one done with a student, Tara Laurila from Helsinki. And if you basically combine these two pieces of work with Anton Burkov's talk, you would expect that indeed there should be some connection. But let me now just leave you with the conclusion.
Thank you very much. There were already a lot of questions. There's already a question by Adolfo. Please go ahead.
Yeah, so very nice talk. Thank you. Very interesting. I mean, a lot of interesting topics. So I can't ask about all of them, but I guess I'm going to kind of rephrase a bit Ronnie's question, which I think, well, she was also in this paper with Fermi arcs. But like my question is that, imagine I have a 3D quantum Hall. So let's say you stack layers of quantum holes, and there we know that the Hall conductivity would be proportional to the lattice vector that is the inverse stacking, right? And so that gives you a scale that is a momentum-like scale, right? And I was wondering, could that enter the conservation equation as lambda squared, because it has the right units, but you won't see it in a low energy description because it's not a lattice. So this lambda squared would, if it's a momentum, it would be presumably defined modulo some lattice vector, and then it's possible that, or the question is it possible, and whether, and then maybe the follow-up question is, could that also be seen as some Fermi arc contribution? That's how I link to Ronnie's question.
Well, I think what you're saying is very likely, but okay, I haven't carefully performed that analysis. But I think what one should do there is that this anomalous Hall response should always be linked to the gapless fermions, basically what Anton was doing in his talk, in the sense that this term it will break gauge invariance if you deform the nodes, and this non-gauge invariance must be cancelled by the gapless fermions. But otherwise, regarding your question, I think it's more about this piece of work applied to semi-metals. So there will be some connection to what I was saying, but okay, remains to kind of explicitly to be worked out.
I guess a different way of asking the question is like, what happens if you actually put this model on a lattice and it's a 3D quantum hole? Like, you cannot get lambda squared because it's a lattice. So would you get 0 or?
No.
I mean,
So,
it's fine if you don't know, but it's just, I'm curious.
So this system is on a lattice, and now basically what you have here is kf squared, and this thing is basically something which is determining kind of the momentum window where your Weyl description or some generalized Newton-Cardan description is valid. And okay, for those theories, you can compute the anomaly, which will be non-zero. And now you would just need to kind of fix the model and see what you can have. And okay, that's all kind of theory. And it's really something where we would need experiments, because you can regularize and present different types of schemes to the anomaly, but there's really only one which matters at the end, which is the one which is realized in nature. So I don't know. But I mean, nothing what I said is kind of, I mean, it should also happen in the lattice, but okay, in the lattice, you can probably, at the end of the day, this UV scale is probably related to, I mean, there are some intermediate scales, but at the end of the day, should be determined by your lattice constant. But I mean, I should emphasize that indeed, from high energy perspective, this is a UV scale, but in condensed matter, the Weyl fermions appear at low energy. So what's UV for low energy is usually not very UV from human perspective.
Thanks.